Hello everybody, I'm Aditya and I'm here to present our lab work on TCP congestion control modification. The objective of this lab is to investigate and enhance the performance of TCP in scenarios involving lossy links by kernel level modifications. We aim to understand how packet loss affects data transfer rates and to develop strategies to mitigate these effects. The focus is explore techniques to differentiate between congestion related packet loss and loss due to unreliable links. Implement modification to TCP stack to improve throughput and reliability during file transfers over high latency and lossy connections. Background: TCP, which stands for Transmission Control Protocol, is a connection-oriented protocol that guarantees reliable delivery of data. It is commonly used for applications where data integrity is crucial, such as web browsing, file transfers, and email. UDP, which stands for User Datagram Protocol, is a connectionless protocol that does not guarantee packet delivery. It is primarily used for applications where speed and low latency are more important than guaranteed delivery, such as streaming, online gaming, and voice over IP. Challenges for TCP: TCP faces several challenges that can impact its performance. Congestion: when network overload occurs, it leads to packet loss. TCP attempts to mitigate this by reducing its sending rate through congestion control mechanism. Loss on unreliable links. Packet loss can also be caused by interference on unreliable links rather than network congestion. In such cases, TCP may misinterpret the loss as congestion and unnecessarily reduce its throughput, leading to suboptimal performance.
I am Krish Modi and I'll be explaining you the AWS topology over which we tested the entire lab. We created a custom VPC at 10.0.0.0/16 CIDR block with dedicated subnets for client server router that are private subnets and are associated with an internet gateway allowing all outbound internet connectivity as needed for each of the three servers that we are going to deploy. We've also deployed multiple network interfaces for the router so that we can map the client only to receive at a particular network interface over the router, and same for the server so that we can manage all the traffic within the VPC through the router for client and server. Route tables are configured to ensure all traffic between client and server is routed via the router VM, while the access to internet is given via the internet gateway that is connected to the subnets and the VPC. Each VM has proper security groups allowing ICMP, TCP, UDP for iPerf, and SSH access for us to access the instance. Finally, you can see the three instances that are deployed. One is router, one is client, one is server, and all the traffic goes through the router for client and server as seen by the network interface setup. We've also allocated the server, client, and router elastic IPs for getting public IPs to access via SSH. And finally, you can see our entire topology in the following diagram to summarize.
So in moving to TCP output.c, so we have 14 changes here. So we initially, instead of min, we just keep the value same. So the idle connections resume with their full initial window. And then the other change here is we have removed um, the max C window, and we have forced C window directly to the configured clamp after restart to immediately reuse the maximum send window. And here, if you can see, so it expands the advertised space instead of clamping, keeping the receiver window large. And here we always advertise a maximum 64 KB initial window even when signed window workarounds are enabled. And we leave the window clamp unchanged, so instead of shrinking it to this scaled size. And here on this we pin non-scaled advertised window to the protocol maximum rather than allowing shrinkage. And here we force the scaled receive windows to the maximum value regardless of scaling. And here we skip the right shift, so window scaling never reduces the window. And here we disable the MTU probe lower bound and keeping the cached MSS as large as possible. That's what's happening here. So we comment it out and keep the value same. So here we avoid decrementing C window and during MTU probes to actually preserve the full sending rate. And here we prevent receiving slow start threshold reductions. And so here we have stopped window rounding to receive window. So receive window can grow without any alignment limits. So that's what we've done. So it forces the SYN-ACK package to advertise maximum 16-bit window. Here. He leaves probe segment size untouched, so allowing full sized window probes. So next we can move on to the input.c, which is the last file. So here we have many changes as well. So here if we see, so we are just forcing the quick ACK budget to the requested maximum. And here we want to grow the send buffer straight to the system limit for more in-flight data. So we stop halving the target window during growth, so keeping the receiver threshold high, receive threshold high. So this immediately raises the slow starts threshold to clamp, so while also expanding the buffers. This keeps initial receive threshold pinned at the clamp after buffer initialization. This line, so we initialize slow start C window and the congestion window clamp for maximum launch rate, and we've just removed the minimum here. and we remove the MTU probe sieve introduction. So that successful probes keeps event at the clamp only. And so yeah, these were the changes in the code. Thank you. We can move on to the next stage. So let's start with timer.c. So starting here, as you can see, instead of exponential timeout calculation, we have just multiplied with a constant multiplier, and we've removed the exponential timeout. And here we have just removed the whole timeout doubling, because we don't want exponential timeout doubling that's happening. And here in this we have again commented out the ping pong mode exit and the minimum ACK timeout as well. And here we have set it to a fixed back off value, which is 5. And also you can see here we have also set it to a fixed retransmit counts. And we've prevented the RTO calculation here. So instead of calculating minimum, we've just kept it to the same value, and we've prevented the minimum RTO calculation. And here again we have done the same thing. Instead of minimum, we've just set it to the same RTO value instead of exponential back off. Now we can move on to TCP.h. So here we have set the max TCP window to a very high value, which is around this value here. And we've also set the fast retransmit on one duplicate acknowledgement. We've set it to 1. And we've also set the fast retransmitting threshold to 1. And here we have set the fast the TCP SYN re-entries to 5. And also this is the max RTO is what we have set, which is around 0.6 seconds. And we have set the min RTO to 0.1 seconds. And we have set the initial timeout to be 0.2 seconds. And we have modified the TCP opt window to 6. So we have disabled the Nagli's algorithm. So we have set it to 0. Now let's move on to TCP Kong.c. So here you can see that we have made changes. It says that we force the maximum congestion window. And here you can see that we prevent window reduction on congestion. So we are preventing that instead of doing this shift, rightward bit shift. So we force a max, we prevent the window reduction. Now let's move on to TCP Vino. So here we aggressively increase the window by 3 in this line. And here we return the max window instead of a reduction of 4 out of 5. Right, we just return the max window. And in this line, we are not deciding to do window halving. Instead, we are keeping it um, the same value, which is TP send CWND, instead of halving the value. Now let's move on to hybla.c. So initially we are forcing the window to be 1 initially, and we also have set the window clamp to be 6250, which is a high value. And here we always use the maximum window, right? We want the maximum window, so that's what we made here. Let's now move on to tcp.c file. So here we have commented this line out. Because it's not needed, and here also we've commented this line out because we don't want to halve the time. We don't want to shift. We don't want to shift the bits in timeout, since we don't need exponential. And here also we have commented out this unlimited congestion window.
Moving on to the procedure to build the kernel. Prerequisites. This guide supports Xenial Xeris and Newer. It is recommended to have at least 8 GB of RAM and 30 GB free disk space on the build machine. If this is your first time you're building a kernel on your system, you will need to set up build environment and install required packages. Set up build environment. To build an Ubuntu kernel, you will need to enable the necessary source repositories in the sources.list or ubuntu.sources file. See how to enable the kernel source package repository for details. Now this is the procedure to install the required packages and the commands followed below. Once done, obtain the source for an Ubuntu release. There are different ways to get the kernel sources depending on the kernel version you want to make changes to. Get kernel source for the version installed on build machine. Use the apt source command to get the source code for this kernel version currently running on your build machine. This will download and unpack the kernel source files to your current working directory. The structure of the directory is shown below. Get the kernel source for the other versions. Use git to get the source code for other kernel versions. Now see how to obtain kernel source for an Ubuntu release using git for detailed instructions. Now prepare the kernel source. Once you have the kernel source, you go to the kernel source working directory. For example, Linux 6.8.0, and run the following commands to ensure you have a clean build environment and necessary scripts have execute permissions. Modify the ABI number. You should modify the kernel version number to avoid conflicts and to differentiate the development kernel from the kernel released by Canonical. To do so, modify the ABI number, the number after the dash following the kernel version, to 999 in the first line of the kernel underscore source underscore working underscore directory / debian.master / changelog file. For example, modify the ABI number to 999 to noble numbat. It would show like Linux 6.8.0-999.48 noble. If you are building something other than the generic Ubuntu Linux kernel, modify the ABI number in the kernel underscore source underscore working underscore directory / debian dot derivative underscore changelog file instead. Now to modify the kernel configuration, uh, to enable or disable any features using kernel configuration, run cd kernel underscore source underscore working directory fake root debian underscore / rules edit configs. This will invoke the menu config interface for you to edit specific configuration files related to the Ubuntu kernel package. You will need to explicitly respond with Y or N when making any config changes to avoid getting errors later in the build process. If the build is successful, several .deb binary packages files will be produced in the directory one level above the kernel source directory. For example, building a kernel with version 6.8.0-999.48 on an x86-64 system will produce the following .debian package and more. Install all the Debian packages generated from the previous step on the build system or a different target system with the same architecture with dpkg-i and reboot. Now this is the output which we obtained on our instance after building the kernel, and you can see that we have the .debian file and all the related packages installed with it. Now the experimental setup, this is the router configuration with a 20% packet loss and rate limit of 100 megabits per second and 200 millisecond RTT. This is the server and client configuration with a rate limit of 100 megabits per second on each server and client. Moving on to the summary of the experiment. After performing the experiment, we were able to achieve a nearly 1.4 megabits per second throughput. The improvements in TCP performance over lossy links were achieved by identifying packet loss sources, congestion versus link reliability, modifying the TCP stack to improve throughput, and sustaining a file transfer protocol transfers at over 1.5 megabits per second under challenging conditions.